Adding an infinite list of numbers together should logically result in an infinitely large sum. But if you take a square, cut it in half, then add a quarter, then an eighth, and continue infinitely, those pieces stack perfectly to fill a finite area of exactly 1. This text definition outlines how mathematics reframes the action for an infinite series. Instead of adding everything simultaneously, we generate a sequence of partial sums up to index n. The series converges only if this sequence of partial sums converges to a single limit. We measure the infinite by observing the pattern of the finite steps approaching it. The series entirely depends on the destination of its partial sums. Because a series is defined by a sequence of sums, the rules for sequences carry over directly. Theorem 3.22 restates the Cauchy criterion for our new partial sums format. A series converges if the sums eventually stop growing further apart. This leads to a strict requirement. Theorem 3.23 states that if a series converges, the limit of its individual terms must be 0. The algebra here is straightforward. If the partial sums are converging to a specific finite ceiling, the gap between consecutive partial sums must shrink to 0. That gap is simply the individual term being added. If the term itself isn't zeroing out, the sum is still moving. Shrinking to 0 is required. It is not, however, a guarantee of convergence. A sequence of terms can shrink toward 0, yet their total sum still pushes to infinity. The classic trap is the harmonic series, adding 1 over n. The individual fractions get infinitely small, but the total sum keeps climbing. The text points to this exactly, citing the harmonic series immediately below the theorem to prove that a limit of 0 is insufficient on its own. Passing this test acts as a preliminary filter. It catches obvious divergences, but it does not equate to mathematical proof of a finite sum. When we restrict our focus to series with entirely positive terms, the logic simplifies. As Theorem 3.24 establishes, because every addition is positive, the sequence of partial sums only goes up. It faces two outcomes. It hits a mathematical ceiling, or it escapes to infinity. We find that ceiling using the comparison test. Theorem 3.25 outlines how we can trap an unknown series by comparing it to the behavior of a known one. If you establish that every term in your target series is smaller than the corresponding term in a known converging series, you have built a roof. The larger series caps out, which forces the smaller series trapped underneath to converge as well. To build those roofs, we need reliable yardsticks. Theorem 3.26 introduces the primary one, the geometric series, where each term is multiplied by a constant factor x. The text proves this by taking the partial sum, multiplying it by x, and subtracting it from the original sum. This causes the massive middle chain of terms to cancel out entirely, isolating a clean algebraic formula for the partial sum. Pause and ask yourself, if x is a fraction smaller than 1, what happens to that x to the power of n plus 1 term as n approaches infinity? It shrinks to 0. The geometric series collapses into a predictable, stable limit, providing the baseline we use to test the stability of countless other mathematical structures. The comparison test works perfectly when you can easily spot a larger ceiling, but what happens when a series steadily decreases, yet resists obvious direct comparison? For decreasing terms, we apply the Cauchy condensation test. Theorem 3.27 presents a highly unintuitive notation. A series converges if and only if the sum of 2 to the power of k multiplied by a sub 2 to the power of k converges. To understand why this works, look at the proof mechanism. We are extracting a thin, targeted subsequence based on powers of 2. We condense the infinite list by grouping terms together into brackets that double in size at each step. 2 terms here, 4 terms there, 8 in the next. Because the terms are decreasing, we can bound the entire bracketed chunk by the smallest term inside it. We replace brute force addition with structural logic. Condensing the series to these power of 2 milestones forces the behavior out into the open to diagnose convergence. Start from the baseline. An infinite series is the finite limit of its partial sums. The terms must shrink toward 0, but that alone is a trap. True convergence requires proving a hard ceiling beneath known yardsticks. These tests provide the tools to verify convergence with precision. They replace visual intuition with a formal framework for determining whether a series terminates at a finite value or grows without bound. If you want to dissect the proofs that build the foundation of modern mathematics, subscribe to the channel. Applying these foundational definitions allows us to move past the ambiguity of adding infinitely many terms. With the partial sums and the Cauchy criterion, we can confirm the stability of a